Okay, good morning. Uh, this is our second lecture, and yesterday we have started introduction to multiphase flow. So, if you recall, what we studied that when we are having association of two or more phases of a substance or two or more components, then we call that system as multiphase system. And the other necessary condition is that whatever the interfacial boundary is there between the components, that interfacial boundary should have variations with space and time. Okay, and typically the interface from macroscopic perspective is a 2D surface. Okay, and in macroscopic perspective we will be having sharp discontinuity in properties across the interface, whereas if we look from the microscopic perspective, then interface comes out to be a volume of small thickness, and in this particular arrangement the variation of properties is actually smooth and continuous across the interface. Okay, and if we talk about the types, then in terms of types actually, two major categorizations we have seen, that some of the flows where two phases can be clearly separated by some interface boundary, that is called as separated two-phase flow, and where the phases are rigorously distributed in one another, that we have called as dispersed two-phase flow. Okay, so some more representations of this kind are shown over here. The reason for showing this representation again is that ultimately in your syllabus you have seen that we have some analytical methods and even in some of the computational methods. So we have different approaches like homogeneous flow modeling, separated flow modeling, drift flux modeling, etc. So depending upon the nature of the flow or the distribution of the two phases, actually we have to select the appropriate model for solving that type of flow situation. So that's why before we are choosing the models for solving this type of problem, we should also clearly know that how our phases are distributed in one another, so that we can select the appropriate model. Because if say I choose some other type of model which is not applicable, whose assumptions are not applicable for a certain flow design, then whatever the outcome we will be getting, that will not be actually true. Okay, so here you can see that transient two-phase flow. So why they are calling it as transient? Because you can see that if we have a pipe surface, then initially within the pipe there are small bubbles, then these bubbles are growing in size, and ultimately this thin film of one phase is created, where the droplets of the same phase are also distributed in the one another. So in this scenario, whenever you are moving across the different cross sections of the pipe, at each and every point we are having some different kind of phase association between the two phases. So that's why we are calling this as transient two-phase flow. On the other hand, if across the entire pipe the flow stays almost in the similar way, then we can simply distribute them in terms of, say, separated and dispersed two-phase flows. So for example, in first case, in separated flow, you can see here we have some clear boundary which is separating liquid and gas. Then another association I am having, where though I am having the chunks of air which are distributed in the liquid, but still the sizes of these chunks are actually big, so that we can clearly make separation between the liquid and the gaseous phase. So wherever during your say systems into consideration, you find this type of behavior where one phase is clearly separated from the other phase, we can simply put them under the category of separated two-phase flow. Okay, and in terms of this type of arrangement, so in first arrangement you can see this liquid is there, and in the liquid we have small gas bubbles present. Okay, so particularly the substance which is present in majority of the system, that particular phase is called as continuous phase, and the one which is distributed into the other, that is called as dispersed phase. So here in this example, the first one, you can see that gas bubbles are actually dispersed within the liquid. So my gas bubbles are actually dispersed phase, and this surrounding liquid is nothing but a continuous phase. Okay, and this is a typical example of dispersed two-phase flow. In the second situation, you can see gas is the continuous medium, and in the gaseous medium, these liquid droplets are actually distributed all across. Okay, so this is an example where gas is a continuous medium and liquid is a dispersed phase, but still this is again in the category of dispersed two-phase flow. And of course, if I am considering the combination of gas and liquid droplets, then it will be an example of gas liquid two-phase flow. Okay, and if I consider that we may have some situations where I am having gas, and within the gas some solid particles are actually suspended. Okay, so these can be even solid particles. So if that situation is there, that all these particles which are dispersed within the gas, these are actually solid, then we will be calling this as gas solid two-phase flow. Is this point clear? So what I want to tell that from this example, we have come to know one more categorization of two-phase flows. And what is that categorization? That categorization is, first I have given the name gas liquid. Okay. Second name I have given gas solid. Likewise, I can have next as liquid solid. Okay. And finally, what I can have a system where all the phases are simultaneously present. So I can even have a system where gas, liquid, solid are simultaneously present. Okay. So if I am calling a multi-phase or two-phase flow problem as a gas liquid two-phase flow. So in this type of problem, always I will be having one phase as liquid and second phase as gas. Can you give some examples of gas liquid flows? Refrigerant flowing through the say copper tubes, particularly in evaporator and condenser, because there in evaporator at the entry point refrigerant is a mixture of liquid plus vapor with low quality. Quality means mass of vapor. Okay, so mass of vapor divided by total mass of the mixture. So, and whenever it is gaining the heat, then that remaining liquid is getting converted into vapor, and finally we have significant amount of vapor. So within that evaporator coil we have combination of liquid and gas present. Okay, then similarly in the condenser, at entry point it is a superheated vapor, and at the exit it is a liquid, saturated or subcooled liquid. So in between the condenser coil I will be having somewhere mixture of liquid and vapor. Okay, then you see your pressure cooker. So in your pressure cooker what we do, we have water, and then once the water reaches the saturation temperature, okay, at the given pressure condition, then that water, if we add further heat, that water start converting into vapor, and we see that vapor fumes coming out of the pressure cooker once the pressure within the cooker is actually exceeding the limit. Okay, so again similarly, when you say if you have get hot water in a pan. So if you put a water in a pan and keep on hitting on the gas stove, then you will be finding after the water is hot, say it has reached to saturation temperature, then bubbles will start coming from the surface of the pan. So again, these are vapor bubbles which are coming and the process is actually boiling. So all these examples are of gas liquid two phase flows. Then can you give me some example of gas solid two phase flow? So atmospheric air is collecting dust. That is actually an example of natural example of gas solid flow. Can you give some examples where these gas solid flows are important and can be utilized for certain applications? Any example? So do you know about coal based thermal power plants? What happens there? We have a boiler. In the boiler we burn coal, and we know that coal is not having 100% volatile material. Okay, so everything is not converting, everything will not participate into combustion and gets converted into combustible gases. Okay, there are certain substances present in the coal which are actually non-volatile and non-combustible. So whenever we burn the coal, all these non-combustible substances are collected in the form of S. So when we burn the coal, then out of that coal, partly we get very fine powdered S, and some of the S is in the form of large size particles. Okay, so the S which is coming out of the boiler, say this is my boiler furnace. So what will be having? Below the furnace we get some large size S particles which are called as bottom S. Okay, and whenever say we allow air to pass through this boiler and then air participate in the combustion process, and when these hot gases comes out of the boiler, these hot gases contain some S particles which are present in that gas. Okay, in these hot gases we have some S particles which are suspended with these hot gases. These S particles are called as fly ash. Okay, now because of the environmental concerns, we cannot directly send all these hot gases to surrounding. So what we do, after these hot gases has supplied heat to the our water, which is getting converted into steam and superheated steam, after that these hot gases are actually passed through some filters. These filters, there are specific type of filters which are used in power plants. So one of the filters are ESPs. What is ESP? Electrostatic precipitators. So there are certain electrodes placed which have charge, and because of their electric field they try to polarize the S particles, and polarized S particles are being collected over the plates of these ESPs and gases actually move across. Okay, then other type of filters which are used are bag filters. So what are bag filters? Again, some material, porous material. Through this porous material, these gases which have loaded fly ash particles, these are passed, and through the pores, gases escape, whereas all these ash particles are gets collected on these filters. Okay, so after these are collected, then we have some cycles in which we try to clean these filters. So what we see at the bottom of the filter, we have actually ash which is in the form of very fine powders, and that particular ash is called as fly ash. Okay, now you see, if you have a 500 megawatt coal based thermal power plant, almost in a day you will be burning the volume of the coal equivalent to that of an entire train. Okay, so this much amount of big volume of the coal you have to actually burn. So once you are burning coal at that large capacity, you will be having lakhs of tons of this ash produced in a both bottom as well as fly, in a single day. Okay, mostly this amount of fly ash and bottom ash present in the coal depends upon the quality of the coal. Okay, and typically whatever Indian coal we have, it contains almost 40 to 50% of non-combustible matter. So it means that if you are burning a single train of coal in a day, then half of that will be, almost half of that will be actually in the form of S, because half of that is containing the non-combustible matter. Okay, so in this scenario you will be finding that whatever the total S we have, out of that 20% will be in the form of bottom S and remaining 80% will be in the form of almost fly S. Okay, so you can see the amount of volume you will be actually obtaining from large capacity plants. Now typically what is done, fly ash is a product which is used for cement making in cement industry. Okay, so typically in all the raw material of cement, once they are in powdered form, in 5% composition actually fly ash is added. So what typically is done in these thermal power plants, in thermal power plants, they use pneumatic conveying systems. Pneumatic conveying systems. So pneumatic conveying systems are air assisted transportation of fly ash particles. Okay, what is pneumatic conveying? Air assisted transportation of fly ash of fine particles or solid particles. So presently for this application we are having fly ash particles. Is this point clear? So typically what is done, there is a pipeline. From the top, this powdered material is allowed to flow down, and from here pressurized air is supplied. What will happen? Particles are flowing down. From here we have pressurized air. We will be finding that in this gaseous medium, these solid particles will be suspended, and this suspension will be transported through these pipelines from one location to another. So typically in a power plant, boiler is located at the core of the plant. So from the boiler location to somewhere near the boundary of the plant, a pneumatic conveying pipeline is there, and this pneumatic conveying pipeline then put this ash in some silo, and from silo this ash is transported in trucks to the applications where it is needed. And sometimes nowadays this ash is also used in brick making. Okay, so what we can see that those say who have done their had a visit to some power plant, you can understand this system that this is how they operate actually, coal based thermal power plants. So over here you can see that gas solid flows are very important in pneumatic conveying applications. Can you tell some other applications of gas solid flows? In pharmaceutical industry. So in pharmaceutical industry, whenever they say make these medicines, so these raw materials typically comes in the powdered form, and the different powders at appropriate composition are allowed to flow from the silos in some reactors, and where these are actually fabricated. So again there you have to transport these particles from one location to another. Okay, then third application could be nowadays when we are having this large scale storage of the food grains. Okay, there also this type of pneumatic conveying arrangements are used. So for example, if you have a silo of somewhere close to 1 lakh liters capacity, and from that silo you want to load your food grain into some vehicle, so what you can do, you can use the automatic arrangement where some conveyor, this type of conveyor will be used for transportation of that uh, food grade. Okay, so this is having applications typically where we have actually solid particles suspended in the gaseous form. Okay, and then other is liquid solid flows. So can you give me some examples where liquid solid flows are present? Phase change materials. Okay, so yes. Abrasive jet, yes. So there are significant applications. So PCMs are nowadays very popular in storing the energy, particularly the solar energy during the daytime and then utilizing it during the night time. So phase change material again will be having the evolution of interface between the solid and the liquid boundary. Okay. Moreover, you can also see that all the sewage line we have. Okay, so in the sewage lines, what we have? We have combination of liquid and solid flows. Then I talked about in the previous example that we have some amount of bottom mass also present in the thermal power plant. So what we will be doing with that bottom mass? So typically this bottom mass is not having any significant application, but it is used to fill the vacant spaces of the coal mine. So it acts as a landfill. So what is done? Typically bottom mass, because it is immediately collected at the bottom of the furnace, so its temperature is actually very high. So what is done? This bottom mass is mixed with water and it is formed a liquid with water. It is formed in the form of a slurry, and that slurry is then transported in the form of pipelines from one location to some sites where this can be dumped. So this particular uh, example will be nothing but of a hydraulic conveying system where water is utilized to convey the solids with water. Okay, so hydraulic conveying systems. More examples are also there. Phase change materials are also the examples. Then another category is gas, liquid, solid. Now, can you tell me some examples where gas, liquid, solid flows phases will be coexisting? Then it will be in the form of gas. Okay. Any other example? You can say in river also, says if solids are eroding and flowing with that, above that there is gaseous phase present. Any other example? Have you heard of the term fluidized bed reactors? So fluidized bed reactors will come under which category? Gas solid or liquid solid gas, or which? Fluidized bed reactor will be coming under the category of gas solid. What is done in case of a fluidized bed reactor? From the bottom, what we have, how this work? So say here I am having some wire mesh kind of arrangement. On this wire mesh kind of arrangement, I have placed the solid fuels, solid particles, and from bottom I have provided the gas. So once I will be providing gas from the bottom, I will choose the gas velocity in such a way so that it suspends these solid particles. It lifts these particles but do not convey with it. It will be only lifting and keeping it in the suspended form. Okay, so this type of reactors are called as fluidized bed reactor. As in case of a fluidized bed reactor, I told you that we will be having gas from the bottom and particles are suspended, so it will be coming in the category of gas solid two phase flow. But there are some other advanced version of these reactors which may not be used for combustion application, for which these fluidized bed reactors are used, but for some other applications in say mineral processing industry. Okay, so in mineral processing industry, what is done, whenever you have the raw minerals in the form of granular materials, these are put inside a reactor, and from the bottom of the reactor we have both water and gas simultaneously flowing from the bottom, and then depending upon their wettability characteristics and their density, different layers of minerals are actually segregated. Okay, so there also you can find some applications if you have advanced mineral processing reactors, that you can have combination of gas, liquid as well as the solid phases simultaneously present. Okay, likewise you can find more number of applications. So here now depending upon the phase association we have given the classification. Other than that, we can have actually two scenarios. Whenever these two phases are coming into existence, these can be either in adiabatic condition. So adiabatic condition, for example, both the phases, if I consider a pipeline, and in the pipeline my gaseous medium is also having the same temperature and the liquid medium is also having the same temperature, but liquid and gas are actually co-flowing with each other. So then we will be having some situation of two-phase flow where there is no heat transfer between the phases, but there will be only existence of momentum exchange between the two phases. So in case of adiabatic two-phase flow, only we will be having momentum exchange across interface. And if I have phase change systems, then I will be having both momentum and heat exchange. Momentum and heat exchange. There can be one another facet of this kind, where if there is existence of chemical potential between the two phases, then because of the chemical potential there can be even species exchange or mass exchange due to difference in the concentration of the species. But for the time being, in this particular course, we will be only talking about momentum exchange and the heat exchange. We will not be referring to the reacting multiphase flows. Okay. So in phase change, again the conditions can be different, boiling and condensation. Most of the applications are listed over here. Then melting, solidification, again the applications are listed, and then sublimation and deposition. So in case of sublimation and deposition, there will be direct conversion from the gaseous phase to the solid phase. Okay. So this slide you can refer. This is just for the information, what are the occurrences and what are the categorizations. Now you see we have different situation. So can you name these phenomenon? What are these? First and second. So both the situations are of pool boiling heat transfer. Okay. And in case of this pool boiling, you can see the first situation where only bubbles are actually isolated bubbles are, vapor bubbles are leaving the heater surface. So this is called as which regime of pool boiling? No, after convection we have nucleate boiling. And the next one is which regime? Transition, or you can see there is a continuous film, so you can call it as film boiling. Okay, so here you can see that we have some thin wire heater surface. From this thin wire heater surface, if the temperature of the heater surface is greater than the saturation temperature of the substance, and say surrounding liquid is nearly at the saturation temperature condition, then we will be having nucleation of these bubbles. But if we increase the surface temperature of the heater surface in such a way so that the bubbles which are growing on the heater surface, then before their departure, if these bubbles are merging with each other, it will be forming a continuous vapor film across the heater surface. Okay, so this is a film boiling. So here you can see surrounding continuous phases, saturated, liquid, and all these bubbles are actually moving as vapor phases, and you can clearly see the boundary between the liquid and the vapor phase. Okay, here this is film boiling. Here this is an example of so this is an example of condensation. So here you can see surface on a surface what is happening in the surroundings of this surface. We have actually saturated vapor. Okay, when that vapor is coming in contact with the surface, it is initially condensed in the form of liquid droplets, and then these liquid droplets are actually leaving the surface. Okay, but we know that initially the condensation process on a surface initiates with what? In the form of droplets, drop-wise condensation, and finally these drops merge together with each other, and after this merging, these form a what? Now you can see the multiple drops will be merging with each other, and finally it will be forming a thin film of liquid. Okay, so this is the now phenomena has transformed from drop-wise condensation to film-wise condensation. However, for achieving the high heat transfer rate, the desired phenomena is drop-wise condensation, because in drop-wise condensation, vapor is directly contacting the solid surface and transferring the heat. In case of film-wise condensation, in between the vapor and the solid surface, there is a thin liquid film, and the additional thermal resistance of the liquid film comes into picture, because of which heat transfer coefficients in film wise condensation are significantly less in comparison to drop wise condensation. So our attempt is always to achieve the drop wise condensation, and in order to achieve drop wise condensation, typically we do some sort of super hydrophobic coatings on the surface, so that immediately whatever water droplet is forming, that should leave the surface. Okay. Next you can see this is a typical application. From here can you see what is happening? So this is a tank, and this is the intake of a pump which is taking water from this tank. Now you can see here this small amount of air is entering, and this air thread is actually being extended even into the intake. Okay. Now, typically our pumps are designed only for operating the pure liquids. Okay, and if the air is going into the pump, then ultimately it can lead to cavitation and erosion of the uh, pump blades, which will be ultimately leading to decrease in overall lifetime of the pump. So this entry of air may not be bothering to a household person, where in our house only we will be operating the pump, say in a day only for half an hour or 1 hour. But if you go to industry, in particularly in process industry, wherever we have to say form some products, what we have to do? We have to allow the different reactant liquids to actually flow at some continuously flow, because plant will be operating round the clock, and moreover the different liquids which we want to react to form some useful product, these should have the controlled flow rates, because we will be allowing them to flow at certain rates so that our reactions and final composition should be correct. Okay, so in these scenarios you will be finding first thing that your pumps operate round the clock, and if in these type of pumps this air entry goes, then overall life of the pump will be very less. Second important point is, if we want to achieve the desired flow rate, if we want to set the flow rate to control certain processes which are existing in the downstream of the pump. Okay, so if entry of air is taking place, this can cause fluctuations in flow rate of the liquid, and if we have fluctuations in flow rate of the liquid, then ultimately we will not be able to achieve our task with the desired composition. Okay, and third important point is, if later on we are using this type of system in some, say, heat transfer equipment. Okay, and in heat transfer equipment, if there is entry of air with the liquid, and if that air is contacting the surface of the solid from where this liquid was getting heat, then ultimately there will be formation of hot spots on the solid surface, because thermal conductivity of the liquid is high and thermal conductivity of gas is low. So when gas is contacting the surface, it will be taking the heat from the surface at lower heat transfer rate, whereas liquid can take heat at high heat transfer rate. Okay, so wherever gaseous contact will be coming with the surface, there the rate at which that heater solid is receiving the heat from the, say, some heat source, it will not be able to dissipate at the same rate to the liquid, and there will be formation of hot spots, and these hot spots sometimes may be detrimental, and if their temperature increases excessively high, it can lead to failure in terms of fracture because of the pressurized liquid present in the system, or because of their melting also. Okay, so you might have seen that uh, in our pressure cooker, we provide one safety feature. Can you tell me the name of that particular device what we use? So that is whistle. If in case your whistle is not functioning due to some reason, say if during the long use of the pressure cooker something has stuck in that particular nozzle, then if that is not functioning, then what happens? Yes, so to safeguard that, we have some small arrangement in the pressure cooker. Safety valve, or we call that as a fusible plug. Have you seen near the pressure cooker, we have a just behind, just below that handle, okay, we have lever of the handle is there. So just below that, we have a small nut attached to that. Okay, what is that? Have you seen this type of hexagonal nut? And then in the center of that, there is some material. Okay, what is this? This is a fusible plug. Okay, once the temperature and pressures gets excessive within the cooker, if your whistle is not lifting, then ultimately it breaks and entire steam comes immediately out. So even after some regular use of the cooker for few years, sometimes we need to replace this. Okay, in certain scenarios, after its long use, it actually gets melted. So this type of system is even used in our boilers also. Okay, so because pressure cooker is having steam at the very less quantity, when you have a big boiler, their steam will be in large capacity. So there not only a single fusible plug is used, but some other safety installation are also done. Then let me also give you one more example. So you can see this first two, three examples are something which have positive effect on occurrences of the two-phase flow. Okay, but this particular example which I discussed here, entry of air if taking place into the liquid, it is having actually detrimental effect. Likewise, there is one more example I have included over here. You can see this. Have you heard of the name Coriolis mass flow meter? So Coriolis mass flow meter is a device which works Coriolis principle. And in this device, what we have this type of two tubes, and these two tubes oscillates, and their oscillation frequency depends upon the mass flow rate of the substance which is or medium which is flowing through these two tubes. Okay, so if mass flow rate is high, their oscillating frequency will be high. If mass flow rate is low, their oscillation frequency will be low. Okay, now uh, in this Coriolis mass flow meter, one effect happens which is called as decoupling effect, and this decoupling effect is an outcome of unwanted entry of air into the liquid mixture. Okay, so here you can see different situations of decoupling effect. So these are the tubes which are oscillating, and now you see. So this is the cross section of the tube, and in this tube, if it is entirely filled with the single phase flow, whatever is actually our desired fluid, then this green colored thing which represents the centroid of the fluid volume. So in this tube, if single phase flow is present, then the centroid of the fluid, and fluid is of homogeneous density, then where will be centroid or center of gravity of the fluid? Center of gravity will be exactly at the geometric center. So this green color is representing center of gravity of the fluid, and this black colored line, if I draw the two diameters, that will be representing the geometric center of this tube cross section. Okay, now if single phase flow is happening, then geometric center of the tube and center of gravity will be actually oscillating at the same with the same center of gravity. Okay, but if there is entry of some foreign substance into this, then what will happen? So here you can see a bubble is present. Okay, and now this bubble, when it is going in upward direction, what it is creating? It is creating low density at the top and high density at the bottom. So centroid of the fluid will be slightly shifting in the downward direction, and you will be finding that there is difference between geometric center of the tube and the centroid. Okay, now, and again, first situation we are considering that though this bubble is present, but the surrounding liquid is actually high viscous. So in this scenario, when these two are oscillating, there is difference between the centroid and this, but this difference is less. Okay. On the other hand, when this liquid will be becoming low density, if instead of high viscosity liquid, if low viscosity liquid is actually flowing, then what will happen? You see now? Now the difference between tube oscillation and centroid of fluid oscillation is actually large. Okay, so basically the tube oscillation, what our transducer outside is measuring, transducer outside is only measuring the tube oscillations, and tube oscillation should match with the oscillations of the centroid of the fluid, then only our reading will be accurate. If there is significant difference between the centroid of the tube and the center of gravity of the fluid present at the cross section, then we will be having error in our measurements. So here again you can see that if a small bubble enters into the liquid medium, then how much it can cause error into our measurements of the mass flow rate if we are using, say, Coriolis type flow meter. Okay, so these are some applications where this type of entry is actually unwanted. Okay, now gas solid flows, as I gave you some idea, here we can have two types of situations. One can be dilute gas solid flow and another can be dense gas solid flow. So in case of dilute gas solid flow, particles will be far apart from each other and suspended only within the fluid medium, so that particle particle interactions are not important. Okay. However, in case of dense gas solid flows, we will be having, you can see the very close arrangement when particles are actually very densely packed to each other. So if I zoom in this portion and make this big frame, then also I can find some clusters of the particles where these are densely packed. And if I further zoom in, here you can see the densely packed particles, and in between the densely packed particles you have, say, some voids. But here particles are so closely packed that particle particle interactions are important. So if you have to analyze dense flow, then particle particle interactions are to be accounted for, whereas the whatever the gas is present in voids, that is having minimal effect on the particle behavior. Okay, because that gas is almost just filling the void space between the particles. It is having excessively low momentum, which is not sufficient enough to change the particle dynamics. Okay, so in dense phase flows, typically if the dense is excessively dense, then gas momentum will not be playing any role. Majorly interaction will be governed because of the particle particle behavior, and if the particles are sparsely placed, these are not having any direct contact, only suspended in the gaseous medium, then momentum exchange between gas and particles will be significantly required for analyzing the entire flow physics. Okay, so maybe we'll stop and then continue from this point in the next class.